Hello students, in this video we are going to go through chapter 2, section 4, which is scatter plots, correlation, and regression. So the key concept here is now we are looking at paired sample datas. So we're looking at things that have two variables, not just one. And we're going to discuss correlation and scatter plots, and then determine linear correlation coefficients. And we will briefly discuss linear regression, which involves the equation and graph of a straight line that best fits sample paired data. So I'm sure this is a lot of new terminology, but it's not too bad. Let's go through it. So scatter plots and correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other. So two events they have some form of relationship. As one goes up, the other goes up, or the opposite could be true. As one value goes up, the other value goes down. One that might have a positive correlation could be, I don't know, the number of hours of work and how much you make on a paycheck. So the more hours you work, the more your paycheck is. So as one goes up, the other goes up. And then other examples might be true where, I don't know, the more you exercise, the lighter you'll be. Might be a negative correlation. And then a linear correlation exists between two variables when there is a correlation and the plotted points can kind of be approximated by a straight line. Think linear, line. Scatter plot is a plot of paired data points. This is just your standard graphing that you did in algebra. You have your xy coordinates, then you plot it on a xy plane, and then you just analyze several different points. So the horizontal axis is for the first variable, x, and the vertical axis is for the variable y. So here is a graph, waist, arm, and correlation. So there is definitely a correlation here because we are saying as someone's waist circumference goes up, their arm circumference also goes up. Each one of these individual red dots represents one data point, one person. So this person right here might have, I don't know, 65 centimeters for a waist circumference, but only a 20 centimeter arm circumference. This guy over here, 170 for waist and 45 for arm. And you can generally see the trend looks like it somewhat resembles a straight line. So that has a linear correlation. This right here represents no correlation. It doesn't seem like it has any kind of general trends, whether that be going up as you move to the right or going down as you move to the right. These seem very random. There's no distinct pattern, so we would say that there is no correlation between weights and pulse rates. They are unrelated events. What if we are somewhere in the middle? Does this have a correlation? I mean, maybe, but it doesn't look like it would be a strong one. But how do we know for sure? So in order to determine if two paired samples have a correlation, we need to determine the linear correlation coefficient, R. Okay, what's a linear correlation coefficient? The linear correlation coefficient is denoted by just lowercase r, and it measures the strength of the linear association between two variables. So here is an extremely complicated formula that I promise I will never make you use. Calculators will do this very, very quickly. But to talk about linear correlation coefficient a little bit much more, is it's going to give you a value that's going to measure how linear data points are. Okay, so using R for determining correlation. So R, when it's computed, is always going to be between -1 and 1. If you have an R value of greater than 1 or less than -1, you did something wrong. So if R is close to -1 or close to +1, then you would say there is a correlation. If R is close to 0, then there does not seem to be a correlation. So let's finding R using technology. So find the linear correlation coefficient of the following data. So we have data pairs 1, 8, 218, 323, 436, 555, and so on all the way to 999. So common sense will tell you, okay, these definitely seem like there's a strong correlation between the two. That red line is kind of that line of best fit. It says fitted line right here, and it definitely seems to be a straight line linear correlation. But let's calculate R using that. Well, we can solve this one of two ways. We can solve it using our TI-84s or using StatCrunch. I'm just going to show you the steps for doing it both ways. So I wrote down the steps for you, but I think I'm just going to show you how to do it as well. So if you're watching the video, you can follow along with my calculator, or if you're just looking at the PowerPoint, then I guess you'll have to read the steps. So I'm going to pause this video for one quick second and resume with the data up. Okay, so I just pulled up the TI-84. If you have a TI-84, like a physical one, follow along with that. If you don't have a physical TI-84, then I sent a link to in a video to how to access an electronic TI-84. It's basically the park test that if you pretend like you're doing a practice one, they'll give you a free version of TI-84 to use. So let's follow these steps. So now we're going to solve R using the TI-84. So first we have to create two lists. So we're going to go to Stat, then hit Enter, and now we have L1 and L2, list 1, list 2. So let's quickly type in our data points. Okay. If you ever want to delete something, you can just highlight it and then hit delete. If you want to delete an entire row, you can just scroll up to the top to highlight L1 and then hit clear right there or delete, and then it'll do that as well. I don't want to do that right now, but just in case. 18, 23, 36, 55, 58, 66, 79, 94, 99. Okay, so now we created two lists. Now we want to calculate R from these two lists. So we're going to hit Stat. We're going to go right 2 times. I want to go to this test up here. And then we're going to go down to F, which is linear regression test. So hit Enter. So the X list I'm going to call L1, the Y list L2, and your version of the TI-84 might be slightly different, but generally just make sure that you are analyzing L1 and L2. Don't worry about this stuff over here. This is actually stats 2, but we're not going to be looking at that right here. So then scroll down to Calculate, and then hit Enter. Okay. So now we have, scroll down a little bit, our R value is 0.9945. So let's go back to our PowerPoint over here. And what did we say? We said if R is close to -1 or +1, there appears to be a correlation. We got 0.9945. So that's pretty dang close to 1. So I would say yes, there is a correlation. Now we're also going to solve R using StatCrunch. Okay, so let's do the same setup before. Someone's going to kind of open up StatCrunch. I should already have it open. We'll do a split screen. Okay, so now we have StatCrunch open. Again, I showed you how to access StatCrunch in an earlier video. So 1, 2, just type in the data. So you can do any of these two methods, whichever one you find easier, or you can do it with Excel as well. The book actually tells you a lot of steps for how doing all of them, but I kind of like just showing you on the video form since that's how I learned, by following along. Okay, so now we have this up here. So we filled in variable 1 and variable 2. Select Stat, Regression, Simple Linear. Stat, Regression, Simple Linear. Have X variable be variable 1 and the Y variable be variable 2. Makes sense. We don't have to worry about all this stuff. We'll actually worry about that in stats 2. And we're going to hit compute. And what do we get? We get the R value, 0.9945. Look familiar? Well, it should, because it is the same value that we got earlier when we did it with the TI-84. If you hit this little next right here, it'll actually give you a graph. And now you know my secret as to where I got this graph right here. But hey, we're all learning together. And that's how you find R. Okay, so let's go back to this example over here. Is there a correlation between shoe print lengths and heights? So here are our actual data values, and here are them graphed. So is there a correlation between the two? Okay, so let's use technology to find R. We don't have to do that ourselves. I'll just give you what R is because I'm trying to prove a point. So when we do it this way, we get a correlation coefficient of 0.5912691. How do we know if that's considered linear? I mean, it isn't very clear if there's a linear correlation. Now, we said that if it's close to 1 or close to -1, there's a correlation. If it's close to 0, there's not a correlation. 0.59 is kind of in the middle, so do you say, oh, it's more than half, so it's correlation? No, we don't. We actually need to find another value. We need to use what's called the critical R value. All right, another term. So what does critical R mean? Now we can blow this back up. The critical R value is the R value that we use to compare our calculated R to when determining if there is a correlation. Okay, so critical R is just a value that we will read from a chart that we will then compare our calculated R to determine if there's a correlation. So this is our calculated R, and then we will do a R from a chart. So critical R is related to the sample size N. So you'll see that on the next slide. We use table A6 or technology to find critical value R. So we say that there is a correlation if the absolute value of R is greater than or equal to the critical value. Then there is a correlation. If the absolute value of R is less than the critical value, we conclude that there is not sufficient evidence. I think that's a very wordy way of explaining it, so let's go right to an example. This visual helps as well. So using table A6 to interpret R, so consider critical values from A6 or technology as being both positive and negative. So again, if your value R falls between the critical value and -1 or the critical value and +1, there is a correlation. And if it's between the two of them, there is no correlation. This graph, I think, this visual, I think, is pretty helpful. So here is table A6, right? A screenshot right from your book. And we are going to be dealing with an alpha of 0.05. We'll actually get to 0.01 later. That's talking about things like confidence intervals and critical values, but we'll just stick with 0.05 for now. And these are the critical R values. So notice how as N increases, R decreases. We're saying that as you have more and more data values, the less and less confident you need to be in order to be conservative. So we compare these critical R values to the one we calculated from our sample to determine if there is a correlation. So these are the numbers that we are comparing our calculated R to determine if there is a correlation. So let's go back to the original example. Is there a correlation between shoe print lengths and heights? Okay, we already determined that we have an R value of R equals 0.5912691. Is there a correlation? We said that we weren't sure. It's kind of in between. So since there are 5 pairs of data, we are going to say that N equals 5. So let's look at now table A6 to see the critical value of R. I told you that we're only dealing with alpha of 0.05. So with an alpha of 0.05 and an N value of 5, boom, 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 play some Battleship, and we have a critical R value of 0.878. Okay, so we calculated R to be 0.591. Our critical value is 0.878. Our R value is smaller than this value. So what does that mean? Uh-oh. since the absolute value, and we only say absolute value because these are both positive and negatives, but in layman's terms, since this R value is smaller than this value, it doesn't work. There's no correlation. If this R value was greater than this critical value, then we're in business. Then there's a correlation. So again, since the absolute value of R is less than the critical value, there is not sufficient evidence to support the claim of a linear correlation. And I kind of made this little visual help as well. So the critical value is positive and negative 0.878. Since our calculated R is 0.591, which is less than right here, so we're in this region, no correlation. Okay, regression. So given a collection of paired sample data, the regression line, or line of best fit, is the straight line that best fits the scatter plot. And don't overthink this. This is just your simple slope-intercept form. You know, your y equals mx plus b, pretty much. So you have all your data points, and then we create our line of best fit, this red line, and we are saying that this, because it's a linear line, will generally have an equation to follow in the form y equals mx plus b, where m is the slope, and then b is the y-intercept. How do we calculate that? Well, we have our calculator do it. So the general form has a, for this example, had a y-intercept of 80.9 and a slope of 3.22. So here is our regression equation. So how do we find that using technology ourselves? Well, we actually already did it. The same exact steps we used to find R actually did this as well. So if you go back to your, I guess I actually still have it up. Let me pull it up to show you that I'm not lying. Okay. Give me one more second. Okay, so this is when we did the linear regression test with the TI-84 to find R. If you scroll up right here, we have A and B. So y equals ax plus, or a plus bx. A is negative 3.866. That's your y-intercept. 10.44 is your slope. Here is your regression equation, right off the same chart that we just did. And then same for StatCrunch. Same exact process. We actually already solved it. I just didn't point you in that direction at that time. So go back to your StatCrunch results over here. Oh. I don't know why it just disappeared on me. Well, you'll see that it says that variable 2 equals this value right here plus 10.44 variable 1. Basically the same values as we got from the TI-84. Okay, so this was the first problem that we were really doing some calculations on. So hopefully you enjoyed this a little bit more. I know I kind of like this class more once we get into real meat and potatoes. And that concludes chapter 2. Any questions, let me know. Thank you.